Welcome to DEEKSHA, Concept-Based Digital Learning. I am Ms.M.Manisha, Degree Lecturer in Chemistry from TSWREIS. Ever since human being came into existence, he started using all the 5 elements of nature, that is fire, water, sky, earth and air for a better living. He started converting all those 5 elements of nature into different forms of energies. So today's topic majorly focuses on one of those elements. Let's do a small demonstration. So rub your hands for 10 seconds and put them on your cheeks. What did you observe or what did you feel? Yes, you felt, and that is heat. So today's topic is nothing but something which is related to heat, and it is thermodynamics. In this topic, the learning outcomes, or at the end of the session, you are going to learn about what is thermodynamics, system and surroundings, intensive and extensive properties, first law of thermodynamics, derivation of Cp minus Cv is equal to R, Joule-Thomson's effect, second law of thermodynamics, entropy and Carnot cycle. Thermodynamics, a science of relationship between heat, work, temperature and energy. In broad terms, thermodynamics deals with the transfer of energy from one form to another form. The key concept is that heat is a form of energy corresponding to a definite amount of mechanical work. As thermodynamics deals with heat, energy and work, let's learn about heat, energy and work. So what is energy, work and heat? Energy is the capacity to do work. Work, transfer of energy. And heat is a form of energy. Units of energy, heat and work are same. That is joules in SI system and calorie. Before studying the laws of thermodynamics and their applications, it is important to understand the meaning of few terms used frequently in thermodynamics. The universe is divided into 2 parts, the system and the surroundings. System is the part of the universe which is under thermodynamic consideration. It is separated from the rest of the universe by real and imaginary boundaries. Everything in the universe that is not the part of the system is called as surroundings. If we consider a closed box containing a conical flask, let's suppose the conical flask is the system and the box is the surroundings. Both together are called universe. System is divided into 3 types: open system, closed system and isolated system. In open system, there is an exchange of both matter and energy. In closed, there is exchange of only energy but not matter. Whereas in isolated system, there is no exchange of either energy or matter. So let's see examples of closed, isolated and open system. So if we consider an open cup of tea, hot tea, there is an exchange of both matter and energy. Hence it is an open system. The next example, as you can see in the picture, is a closed cup of hot tea. So there is exchange of only energy but not matter. Hence it is a closed system. The last one is a thermoflask. There is no exchange of either energy or matter. Hence it is an isolated system. So let's study about intensive and extensive properties. Intensive properties are the physical properties that do not depend on amount of matter. Extensive properties are the physical properties that do depend on amount of matter. Intensive properties are independent of amount of matter. Extensive properties are dependent on amount of matter. Some of the examples of intensive properties are melting point, boiling point, density, etc. Some of the examples of extensive properties are volume, mass, energy, etc. So these are the major examples of intensive and extensive properties. So under intensive properties, the examples are pressure, temperature, density, concentration, melting point, boiling point, surface tension, viscosity, etc. Under extensive properties, the examples are mass, volume, internal energy, heat capacity, enthalpy, entropy, Helmholtz energy, Gibbs free energy, etc. So let's study about state function and path function. Property of a system which depends mostly on a present state of the system but not on the path is called as state function. The property of a system which depends only on the path during the change is called as path function. So as you can see in the picture, there are two pictures. In picture 1, there are two paths, x and y. In this example, state function considers the initial and final points only, that is base and summit. And the path function is the path taken to reach that point. And in the picture 2, there are two paths, AF, that is A final, and A initial, AI. State function is initial and final points only, that is delta A only, whereas path function is the path taken to reach that final point. So some of the examples of state functions are delta H, change in enthalpy, delta G, change in Gibbs free energy, delta V, change in volume, and delta T, change in temperature. And examples of path function are work and heat. So let's study about first law of thermodynamics. So according to first law of thermodynamics, energy can be neither created nor destroyed, but it can be transformed from one form to another form. That is first law of thermodynamics. So the equation of first law of thermodynamics is delta U is equal to Q minus W. So where delta U is change in internal energy, Q is the heat and W is the work. So this picture, transformation of one form of energy into another form. That is transformation of chemical energy into kinetic energy. So these are the examples of conversion of first law energy. These are the examples of first law of thermodynamics. This is the equation of first law of thermodynamics. Delta U is equal to Q minus W. So let's do a small problem on first law of thermodynamics. So the question is, what is the change in internal energy of a gas if it takes 3000 joules of heat while it does 1000 joules of work? So in the question, they have given heat as 3000 joules and work as 1000 joules, and they are asking for change in internal energy. So we will know that delta U is equal to Q minus W. So if we substitute the values, 3000 joules minus 1000 joules is nothing but 2000 joules of internal energy is the answer. So let's study about molar heat capacity. So molar heat capacity is the heat required to raise the temperature of 1 mole of gas by 1 degree Celsius or 1 Kelvin. So the heat capacity of gas in two states is different. One at constant pressure and other at constant volume. So Cp is equal to delta Q by delta T and Cv is equal to delta V by delta U by delta T. So this picture shows the beaker containing molar capacities, molar heat capacity at constant volume and at constant. So the first beaker shows as the molar heat capacity at constant volume, where the volume is constant. And the second beaker shows us the molar heat capacity at constant pressure, where the pressure is constant. So let's study about derivation of Cp and Cv. That is, Cp minus Cv is equal to R. Cp is defined as the molar heat capacity of a gas at constant pressure. Cv is defined as a molar heat capacity of a gas at constant volume. These molar heat capacities are interrelated with R. So Cp minus Cv is equal to R. How did we get that relation? So as we know, molar heat capacity at constant pressure, Cp is equal to delta Q by delta T. But according to first law of thermodynamics, delta Q is equal to delta U plus P delta V. So Cp is equal to delta U plus P delta V. But according to first law of thermodynamics, delta Q is equal to delta U plus P delta V. So if we substitute this delta Q in Cp, so Cp is equal to delta U plus P delta V by delta T. And separating the terms, substituting Cv and R in the related terms, we are going to get Cp minus Cv is equal to R. So the next topic is Joule-Thomson effect, one of the most important topics. So the phenomena was investigated in 1852 by British physicists James Prescott Joule and William Thomson. Joule-Thomson effect refers to the change which takes place in fluid's temperature as it flows from the region of higher pressure to lower pressure adiabatically. The change in temperature that accompanies expansion of a gas adiabatically without production of work or transfer of heat. At ordinary temperatures and pressures, all real gases except hydrogen and helium cool upon such expansion. This phenomenon utilized in liquefying gases. The cooling occurs because work must be done to overcome the long-range interactions between the gas molecules as they move farther apart. Hydrogen and helium will cool upon expansion only if their initial temperatures are very low, because the long-range forces in these gases are unusually weak. So this picture shows the Joule-Thomson experiment. So in the Joule-Thomson experiment, a constant flow of gas was maintained along a tube which was divided into two compartments separated by a porous plug, such that the pressure and the molar volume on the upper stream side are P1 and V1, and the pressure and molar volume on the downstream side were P2 and V2. The temperatures T1 and T2 are measured. When the gas flows from a region of high pressure to low pressure, change in temperature is observed. Mostly the temperature is cooled. So these are the following results that are observed from Joule-Thomson effect. All the gases show change in temperature when they pass through the porous plug. The change in temperature is proportional to difference in pressures P1 and P2. At ordinary temperatures, hydrogen and helium were warmed up. Every gas shows a characteristic temperature above which gas gets warm. Below that temperature, the gas gets cooled. That particular temperature the gas gets cooled is called inversion temperature. Most of the gases, except hydrogen and helium, shows cooling effect. It is due to decrease in kinetic energy of gaseous molecules during expansion. So there are many applications of Joule-Thomson effect. Some of the examples of Joule-Thomson effect are refrigerator, AC, and Joule-Thomson effect is mostly used in liquefying gases. Let's study about second law of thermodynamics. Second law of thermodynamics gives more information about thermodynamic process. It is defined as heat cannot flow itself from colder body to a hotter body. The second law is also used to determine the theoretical limits for the performance of mostly used engineering systems like heat engines and heat pumps. So let's study about entropy. Entropy. What is entropy? Generally, entropy is defined as a measure of randomness or degree of disorderness. So it is basically the disorderness of a system. This concept was introduced by a German physicist named Rudolf Clausius in the year 1850. So in this picture, you can see the degree of disorderness. Degree of disorderness is high in the first and later on it decreased. This is another picture or another example of entropy where there is increase in degree of disorderness. Properties of entropy. It is a thermodynamic function. It is a state function. It depends on state of the system but not on the path. It is represented by S, but in the standard state it is represented by S naught. Its SI unit is joules per Kelvin mole and CGS unit is calorie per Kelvin mole. Entropy is an extensive property which means that it scales with the size or extent of a system. Carnot cycle. The Carnot cycle is a thermodynamic process that describes how a fluid is used to convert thermal energy into work. It is related to the theory of heat engines. Carnot devised an ideal cycle of operation for a heat engine and is known as Carnot cycle. In one complete cycle of operation, there are 4 different thermodynamic processes. Let's study those 4 different thermodynamic processes of Carnot cycle. First one is isothermal expansion. At first, the working substance is kept in contact with the source. The piston of the cylinder is moved outwards. The gas expands at constant temperature. The amount of heat is absorbed from the source to make the temperature constant. The volume increases and the pressure decreases. This is isothermal expansion. It is represented by the curve AB as it is indicated in the diagram. So this is the diagram of isothermal expansion. The curve AB represents the isothermal expansion. The second one is adiabatic expansion. The lower conducting side of the cylinder is kept in contact with the insulating stand. The piston of the cylinder is moved outwards. The gas expands such that no heat enters the system or leaves from it because it is adiabatic. The volume increases and the pressure decreases. The temperature is decreased from T1 to T2. This is called as adiabatic expansion. This curve shows us the adiabatic expansion. The curve BC shows the adiabatic expansion. So the third one is the isothermal compression. The cylinder is kept in contact with the sink. The piston of the cylinder is moved inwards. The gas is compressed at constant temperature. The excess heat produced Q2 will flow into the sink to make the temperature constant. The volume decreases and the pressure increases. This is called isothermal compression. So the diagram represents the isothermal compression. CD. is the isothermal compression. The last one, adiabatic compression. The cylinder is kept in contact with the insulating stand. The piston of the cylinder is moved inwards. The gas is compressed such that no heat enters the system or leaves from it. The volume decreases and pressure increases. The temperature increases from T2 to T1. This is called as adiabatic compression. The graph DA shows us the adiabatic compression. So this complete cycle A, B, C, D is called as Carnot cycle. Major points that are to be remembered from Carnot engine are: Carnot engine is purely an imaginary engine, but all real engines are constructed based on Carnot cycle. No other engine can have same efficiency as that of a Carnot engine, working between the same temperature range. So characteristics of Carnot engine are: high efficiency, it is a multi-source engine, better reliability and easier maintenance, reversible, it is safe, discreet and oxygen free, modularity and flexibility. Most of the engines have thermodynamic limit of 37% only. Practical efficiency depends on temperature, level and differences. Waste heat is easily harvested, making Carnot engines useful for dual output, heat and power systems. So multi-source engine. Carnot engines can run directly on any available heat sources. They are used in solar panels, they are used in industries and other heat-related sources. So these are the major applications of Carnot engines in our day-to-day life. Let's learn about third law of thermodynamics. At absolute 0 Kelvin temperature, theoretically, all modes of motion stops. That is, no vibration, no rotation and no translation. Thus, third law of thermodynamics states that the entropy of a pure crystalline substance at 0 is 0. Applications of thermodynamics are: it is seen everywhere, mostly in human body, air conditioning systems, aeroplanes, refrigerators, car radiators and power plants. So the summary of today's session is: today we have learned about thermodynamics. Thermodynamics is science and the relationship between heat, work, energy. We have studied about system and surroundings. Under system, we have studied about open system, closed system and isolated system. Next, we have studied about intensive and extensive properties. Intensive properties are the physical properties which are independent of amount of matter. Extensive properties are the physical properties that are dependent on amount of matter. Next, we have studied about state function and path function. State function depends only on the initial and final states, whereas path function depends on the path of the system. We have seen various examples of state function and also path function. Next, we have studied about first law of thermodynamics. So, according to first law of thermodynamics, energy can be neither created nor destroyed, but it can be transformed from one form to another. We have also seen the examples of first law of thermodynamics. So, the equation of first law of thermodynamics is delta U is equal to Q minus W, where delta U is change in internal energy, Q is heat and W is work done. Next, we have seen the derivation of Cp minus Cv is equal to R, where Cp is called as molar heat capacity at constant pressure and Cv is called as molar heat capacity at constant volume, and R is called as gas constant. So we have seen the derivation of Cp minus Cv. Next, we have seen the Joule-Thomson effect. So under Joule-Thomson effect, cooling of temperature is seen when a gas is allowed to move from a region of high pressure to low pressure adiabatically. And there are many examples of Joule-Thomson effect. One of the most important examples is fridge, that is refrigerator, AC, and it is mostly used in liquefaction of gases. Next is second law of thermodynamics. So according to second law of thermodynamics, heat cannot move from a region of colder body to hotter body. It is impossible for heat to move from a colder body to hotter body. So that is second law of thermodynamics. Next, we have seen entropy. Entropy is the degree of disorderliness. So if we consider solid, liquid and gases, in solid, the degree of disorderliness is very less compared to liquids, compared to gases. In gases, degree of disorderliness is really large and the entropy in gases is really high. Next, we have seen Carnot cycle. So under Carnot cycle, we have seen 4 thermodynamic properties. One is isothermal compression. Second one is adiabatic compression. Third one is isothermal expansion. And fourth one is adiabatic expansion. So we have seen all these thermodynamic relations in Carnot cycle. And Carnot cycle is mostly used in industries, in heat engines and heat pumps, etc. And lastly, we have seen third law of thermodynamics. So these are the summary points of today's session. I want to conclude that thermodynamics is considered to be one of the most important parts of our day-to-day life. Whether you are traveling in any vehicle, sitting comfortably in your air-conditioned room, watching television, etc., you will notice the applications of thermodynamics almost everywhere, directly or indirectly. I hope this session is very useful to you all. Thank you.